Hello and welcome to today's lesson on nuclear decays, which is part of the particles and radiation topic in AQA A-Level Physics. So in today's lesson we're going to try to understand the processes behind alpha decay and beta decay. Now if we're successful and we learn in today's lesson, we should be able to describe alpha decay and beta decay, illustrate alpha and beta decay using equations, and deduce why the neutrino is necessary in beta decay. Now in a nuclear decay, nuclei change from unstable nuclei into stable nuclei. Now most processes by which this takes place is the weak interaction. So in this case the W boson is passed from the unstable nuclei to their stable products. Now the decay process lessens the impact of the electromagnetic interaction and increases the strong interaction. It normally does this by decreasing the nuclear radius, so the strong force has a greater impact. So the only exception to this idea is alpha decay, as it doesn't involve leptons or particles change in type, so it decays via the strong interaction. So this therefore means alpha decay is a very fast interaction compared to beta decay. Now in the previous example we considered a radioactive nucleus to be an unhappy face, but in reality it's more appropriate to say a radioactive nucleus is like a bubbling volcano. It's constantly churning and turning, waiting to erupt and emit a form of radiation. But what causes this instability? What causes the nucleus to decay? What interactions are found in the nucleus? So there are two interactions which affect the stability of the nucleus. The strong interaction, which causes attraction between all the nucleons, and the electromagnetic interaction, which causes repulsion between all of the protons. But what are the size of these interactions in stable and unstable nuclei? So to achieve a stable nucleus, the strong interaction must be larger than the electromagnetic interaction. Now again, for a stable nucleus, our idea is the strong interaction is much greater than the electromagnetic interaction. Now remember, the strong interaction causes attraction between all nucleons, but the electromagnetic interaction only causes repulsion between the protons. Now if you're unstable, the strong interaction is approximately the same as the electromagnetic interaction. So in theory, every nuclear decay tries to increase the magnitude of strong interaction compared to the electromagnetic interaction. Now, a decay process can be thought of as a snowfield on a mountain. While the friction between the ice crystals may be supporting the snow's weight, the system is inherently unstable and wants to go to a state of lower potential energy. This is the concept of entropy. Objects tend to states of lower energy. So to do this, the snow would have to crumble, relax and release energy. Now a disturbance would facilitate the path to a greater entropy disorder. So this is very similar to an unstable nucleus due to the electromagnetic and the strong interactions being equal to each other. So the radioactive nucleus will move towards the ground state or the stable state, and radioactivity decay producing energy or particles. So the total energy will be distributed over a larger number of quantum states. It's the idea equivalent to an avalanche. Now avalanches have been observed in one direction, and that's towards the ground state, the state with the largest number of ways in which the available energy could be distributed, i.e. the snow is spread over a larger area. And this is the same with radioactive nuclear decays. Now a radioactive decay needs an activation energy to start it, like a spark causes a fire. So for a snow avalanche, this energy comes as a disturbance, like a noise or a movement. But in the case of an excited atomic nucleus, the arbitrarily small disturbance comes from the particle interactions between the nucleons and the exchange of a boson. Now the similar size of the interactions, the electromagnetism is approximately equal to the strong interaction in the nucleus, means that a small disturbance can cause this decay. Now in certain cases, the random quantum fluctuations are theorized to promote the nucleus relaxing to a lower energy state or decay in a phenomenon known as quantum tunneling. But what are the different types of decay found in particle physics? Well, this idea is revision from GCSE physics. There are three major types of radioactive decay which occur in unstable nucleus. Alpha decay, beta decay and gamma emission. So you've got three possible pathways in which an unstable nucleus can decay, but in actuality there are two types of beta decay which can take place, and there's a fourth decay process which can also occur called internal conversion. So alpha radiation is the release of an alpha particle, and this occurs in large elements like uranium and radium, and an alpha particle is made of 2 neutrons and 2 protons, so it's got an overall charge of +2 and an atomic mass of 4 atomic mass units. Now, as you've learned in GCSE, the alpha particle does not travel very far, so the best way to protect yourself from alpha radiation is to keep yourself half a metre away from it use clothing or a face mask. Now, this process occurs due to a strong interaction, as it only involves quarks, and it happens with the exchange of a gluon, which is why the alpha decay occurs quickly. Now, in beta, a beta particle is emitted when a neutron in the nucleus changes into a proton, releasing a negative charge in the form of a fast-moving electron. It has an overall charge of -1 and a negligible mass, about 1/2000th of an atomic mass unit, and this process occurs due to the weak interaction, as it involves leptons and the baryons change in type, and this occurs due to the exchange of a W boson, which is why the beta decay is a slow interaction. And finally, after a nucleus has emitted an alpha particle or beta particle, it may still have too much energy to be stable, so we say it's in an excited state. So to get rid of this energy, it can be released by emitting a very high frequency photon called a gamma ray or a gamma photon. Now, these gamma photons have no mass or no charge, but it's very penetrating, has a very long range, so to protect yourself you would need at least 10 centimeters of lead or be quite a long way from a gamma source. So at GCSE you learned about the following properties of alpha, beta and gamma radiation, which is very important. Now, we need to be able to write nuclear equations to show alpha and beta decay. Now, the symbols in the periodic table allow you to work out the number of protons and neutrons in a nucleus. So A, the upper number, is the atomic mass, which is the number of protons and neutrons. Z is the atomic number, the lower number, the number of protons, and X is the chemical symbol as shown on the periodic table. So in alpha decay, 2 protons and 2 neutrons are lost from a nucleus when it emits an alpha particle, so its atomic mass number has decreased by 4 and its atomic number has decreased by 2. So in alpha decay, a new element is formed that is 2 places lower in the periodic table than the original element, so as you can see in the following decay equation. So, in alpha emission, an alpha particle, a helium nucleus, is ejected from a parent nucleus. So, in the nucleus, there's a loss of 2 protons and 2 neutrons. So, there must be a new element formed since there's a different number of protons. And whilst this alpha is actually a helium nucleus, the term alpha is used if the particle is originated from the nucleus. So, this is an example of transmutation, as a new element is formed in the existing nucleus. Now, the element formed from alpha decay is found 2 places lower on the periodic table than the parent element. Now, each alpha particle is released with the same kinetic energy, as there are no other products produced in the decay. So this is a demonstration of alpha emission. Now, in beta decay, a neutron changes into a proton and an electron. The proton stays in the nucleus, the electron leaves the atom with a high energy as a beta particle. So the nucleus has 1 more proton and 1 less neutron when it emits a beta particle. So the atomic mass number, the number of protons and neutrons, stays the same, but the atomic number increases by 1. Now, this must need the weak interaction, as it involves leptons and particles change in type. So what we can find is, when we look at our nuclear decay equation, it indicates that this process can produce a new element 1 place higher in the periodic table than the previous. So in beta minus emission, a neutron is transformed into a proton that stays in the nucleus and an electron which is emitted. Now, beta minus emitters are found naturally in the universe, but they can also be manufactured with stable isotopes being bombarded and absorbing neutrons. Now, there is a new element formed since there's a different number of protons in the nucleus after beta minus emission, and whilst this is the same as an electron, the term beta is used for the electron emitted if the particle has originated from the nucleus. Now, again, this is an example of transmutation, as a new element has been formed in the nucleus. Now, the element formed in beta minus emission is found 1 place higher on the periodic table compared to the parent nucleus. Now, beta minus emitters, like we said before, are found naturally in the universe, and this is an example of beta minus emission. Now, you can, as well as getting beta minus emission, which you learned at GCSE, you can actually get the opposite beta decay process to take place as well, and that is the beta plus emission, which when a proton is transformed into a neutron and a positron. Now, beta plus emitters are not found naturally in the universe, but they are manufactured with stable isotopes being bombarded and absorbing protons. Now, again, like beta minus emission, beta plus emission forms a new element since there's a different number of protons in the nucleus. And again, we call this a beta particle, but it is in fact an electron, and we only give it the name beta when in fact this electron originates from the nucleus. And again, it's an example of transmutation as a new element is being formed. And the element form of beta plus emission is found one place lower on the periodic table to that of the parent nucleus. Now, in gamma decay, there is no change in the makeup of the particles, it just loses energy from the nucleus in terms of photons. So gamma emission is as follows. Alpha emission is often followed by gamma ray emission. The daughter nuclei are left in an excited state which will at some point fall to the ground state, emitting a gamma photon. And there's no nuclear structure change, there's just a change of energy. Now, this is not an example of transmutation as no new element is formed. There is no nucleon change. Now, a nucleus which has excess energy before gamma decay is in what we call a metastable state. So this is a demonstration of gamma ray emission. Now, it's important to note that gamma emission can only really occur after alpha emission has taken place. So it's important to note that they are complementary processes to each other. Now, we can see the idea of gamma decay in the following equation, that it's the same element as you have the same number of protons before and after the decay, and the gamma energy is a photon of a high frequency, and remember, a photon has no charge or mass. Now, we can represent the radioactive decays and the change that they cause with a decay path diagram. And now this shows how the neutron number and the proton number change in a decay. Now, in reality, an unstable nucleus will undergo a number of different radioactive decays before it becomes stable, which is actually shown on a radioactive chain decay diagram, which is a chain diagram as each decay is linked to the previous decay for the nucleus. So the path the unstable nucleus will take is shown on the decay chain, the decay path diagram. Now, you'll notice that there can be a variety of paths which the unstable nucleus can take, and the path that they do take is down to probability. Now, in addition, a comprehensive decay chain diagram will also include the half-life of the decay processes. Now, we can recap the nuclear decay processes information with the following ideas. An unstable nucleus will increase stability and turn into a more stable nucleus when it carries out a decay. Now, the most well-known type of decay is alpha decay, when the nucleus loses 2 protons and 2 neutrons. So therefore, this will occur in large isotopes, and this increases stability as the nuclear radius decreases, increasing the impact of the strong interaction on the nucleus. Another well-known example from GCSE to increase stability is beta minus decay, which is when the unstable nuclei will lose 1 neutron, gain 1 proton, and emit 1 electron. Now, this occurs in isotopes with too many neutrons. Now, beta minus emitters can be produced by bombarding a nucleus with neutrons. Now, this increases stability as it reduces the quantum fluctuations due to the excess neutrons found in the nucleus. Now, it's important to also note that the opposite of beta minus decay is beta plus decay, which is where you gain 1 neutron, you lose 1 proton, and you emit 1 positron. Now, again, this occurs in isotopes with too few neutrons. So beta plus emitters can be produced by bombarding nuclei with protons, which is actually a bit harder to do than bombarding with neutrons, as there'll also be the effect of electromagnetic repulsion. Now, this increases stability as it reduces the electromagnetic repulsion because you've lost a proton, yet increases the attractive strong interaction. Now, the final well-known example from GCSE physics is gamma emission. So in this point, the unstable nucleus will increase stability by releasing gamma radiation in forms of photons. So this occurs in isotopes which have too much energy in their structure, and this tends to occur in nuclei which already have carried out alpha or beta decay. So it occurs in isotopes that have just too much energy. So when physicists examined alpha and beta decay in more detail, there was an issue in the amount of energy produced in the decay processes of each one, because in alpha decay, alpha particles are emitted with a well-defined energy. Each alpha particle always has the same amount of energy as each other. So each alpha particle is produced with the same rest energy and the same kinetic energy. So all alpha particles travel at the same speed. So this obeys the conservation of energy and mass in the decay process, which is important. Now, again, in gamma decay, gamma photons are emitted with a well-defined energy. So it again obeys the conservation of energy and mass. But in beta decay, beta particles are emitted with a range of energies. And this was against the conservation conservation of energy, because some beta particles might have kinetic energies of 10 eV, some 13 eV, some 15 eV. Now each beta particle is produced with the same rest energy, but there's a variation in kinetic energy, so beta particles are emitted with different speeds. So this looks like, in fact, there's a violation in the conservation of energy and mass. So was our understanding in physics wrong? So why did the emitted beta particle have a range of possible energies? Was some energy just lost out of the universe? Does this go against the laws of thermodynamics? Now this was known as the beta decay problem. So what was the reason why beta particles are emitted at different speeds? Now in 1930 this problem was a hot topic of physics, and it was solved by the famous physicist Wolfgang Pauli. Now in 1930 Wolfgang Pauli suggested it in a famous letter to fellow physicists starting, "Dear Radioactive, ladies and gentlemen," he wrote, "I've done something terrible. I've predicted an undetectable particle." So Pauli solved the beta decay by suggesting whenever a lepton is produced, and in this example an electron or a positron, a neutrino was also produced. But he considered the neutrino to have no charge and no mass. So he did something unthinkable. He predicted a particle with no rest mass and no charge. So how are we going to detect it? Now he originally called the particle the neutron, but it was renamed the neutrino because this became the accepted name when in 1932 Chadwick had discovered a much larger neutral component of the nucleus that better deserved the name neutron. So Pauli suggested that the lost energy in beta decay was carried away by a new particle, so that the total energy of a beta decay is constant. But this particle is chargeless and has virtually no rest mass. Now Enrico Fermi developed the theory of this new particle, which he called a neutrino, but it wasn't until 1951 that it was discovered in the Savannah River nuclear detector in America. Now the rest mass of the electron neutrino is only 3 eV per c squared. But the electron has a rest mass of 0.511 MeV over c squared. So even compared to the electron, a traditionally particle which is thought to be very, very small compared to protons and neutrons, the neutrino is on the order of 100,000 times smaller than the electron. So the rest mass of the neutrino is much smaller than the rest mass of the electron. So Pauli realized that the total energy before the beta decay equaled the total energy after the decay. However, the total energy before was the energy of the unstable nucleus, but the total energy after was the energy of the stable nucleus, the energy of the beta particle, and the energy of the neutrino. So this was solved the beta decay problem, because if there was no neutrino produced, then the energy was not conserved, because the neutrino takes some of the energy. So that is why it appears that the beta minus, the electron, is being emitted with a variety of energies, because the neutrino is taking away some of that energy. So the neutrino energy comes from the kinetic energy of the beta. So as the neutrinos take different energies, the beta particles have different energies to ensure the total energy is the same. So this can happen as the neutrino takes the energy from the kinetic energy of the beta particle, so it means the larger the neutrino, the slower the beta particle. Now Pauli later realized that the neutrino produced for a lepton is actually an anti-neutrino, and this is due to conservation laws, which we'll look at next lesson. It's the idea that you've got to conserve the lepton number. So it's an important idea that we need to consider. So like the electron and the muon, neutrinos have antiparticles, and furthermore there are different neutrinos associated with the electron and the muon and the tau. So as a result, because these light particles do not experience a strong interaction of hadrons, they form a different category of particle and are given the name leptons. So we now know that there are 12 leptons: the electron, the tau and the muon, and the neutrino for each one of these, and their equivalent antiparticles. So as a neutrino has always been observed to be produced when a lepton is produced, physicists have said it's like a dog with a flea. Whenever there's a dog, there's always a flea. Whenever you produce a lepton, there is always a neutrino. So we can amend the previous beta decay equations to include the following. So in the beta minus emission, a neutron is transformed into a proton and an electron, but it also emits emits an electron anti-neutrino as well. So the beta particles can be emitted with a variety of kinetic energies due to the anti-neutrino also produced. Now it's important to note the neutrino produced must be an anti-neutrino to conserve the lepton number of this decay process. Now in beta plus emission, okay, we know that this is an example of transmutation as a new element is formed, but the beta particle can be emitted with a variety of kinetic energies due to the neutrino also being produced. Now the neutrino produced must be a standard neutrino due to the conservation of lepton number. Now in addition to the traditional decays of the nucleus, there's a fourth nuclear decay, internal conversion. So internal conversion is a process in which a nucleus in an excited state can release its excess energy. Now in internal conversion, all of the excess energy is transferred from the nucleus to an orbital electron through the electromagnetic force. This orbital electron is then ejected from the atom. Now both internal conversion and beta decay will eject electrons from the nucleus, but there are many differences between internal conversion and beta decays, because beta decays occur via the weak interaction, but internal conversion occurs via the electromagnetic interaction. Beta decays also produce neutrinos or antineutrinos in the process, but internal conversion will only eject an electron. In beta decays, you'll produce a nucleus of a new element because your proton is turned into a neutron or vice versa, but internal conversion does not do that. Number 4, in beta decay, electrons are emitted with a range of energies, but due to the neutrino or antineutrino also being produced. But in internal conversion, all electrons have the same energy. And finally, in beta decays, the electron is emitted from the nucleus, but in internal conversion, the electron is emitted from a shell. So what have we learned about in today's lesson? We've looked at unstable nuclei, alpha and beta decay. We've looked at the equation for alpha decay and beta decay, including the need for the neutrino, and understanding that the existence of the neutrino was hypothesized to account for the conservation of energy in beta decay. So if we've been successful and learned in today's lesson, we should be able to describe alpha and beta decay, we should be able to illustrate alpha and beta decay using equations, and finally deduce why the neutrino is necessary in beta decay. I hope you've enjoyed today's lesson on nuclear decays, which forms part of the particles and radiation topic in AQA A-Level Physics. Thank you very much for listening to today's lesson, and have a lovely day.